Okay, now let's do 3.6. Always, sometimes, nevers. Oh my gosh, am I excited to see these. You guys, so good. Circle whether each statement is always, sometimes, or never true. Let's see. If a 0 has an odd multiplicity, the function passes through the x-axis. Let's go through this real quick, okay? I know we can definitely always use a little bit more practice and a little bit more me explaining it. I'm gonna kind of re-explain the concept of the zeros and the multiplicities, all right? When I have a polynomial, you guys, if we look at that polynomial in factored form, like this, I can have like x minus 5. I'm sorry, let's make it plus. X plus 5. X minus, no, let's go plus 1. And let's go x minus 3. This right here means that I've got a 0 at -5. I've got one at -1. And I've got one at +3. These are the zeros. Okay, so -5, let's say that's there. -1. Ooh, I wrote 5 again. And then 3. Now, right now, the way that these guys are, they're all a multiplicity of 1. Multiplicity just means that 0, how many times does it occur? Right now, they each only occur once. But if I go ahead and put a 2 on that one and a 3 exponent on that one, well, now that 0 appears just once. That one appears twice, because this is really x plus 1 times x plus 1. And that one is appearing 3 times, x plus 1. I'm sorry, x minus 3, x minus 3, x minus 3, 3. These are called the multiplicities. All right, so -5 has a multiplicity of 1. -1 has a multiplicity of 2. And 3 has a multiplicity of 3. Okay, now last little part of this. What the heck does the multiplicity mean? All right, we found it, figured out what it is, but what does it mean? So the 1, you guys, means that this function right here, around this -5 x-intercept, right in this little small vicinity, it behaves like x plus 1 to the first power, x plus 5 to the first power. X plus 5 to the first power, that's a y equals mx plus b equation. So it's a line, all right? Which means this function right here looks like a line, all right? Just in the immediate vicinity around the x-intercept. And this one, with the multiplicity of 2 for -1, it's going to behave like x plus 1 squared, all right? So I know I'm coming at it this way. It's going to look like a quadratic, so a parabola, okay? And then lastly, oh, wait, I did this all wrong. Hold on, mistake. But my mistake is a 3.7 mistake. I was trying not to focus on that right now. You guys, we're going to explore why what I'm about to say is true in the 3.7 one, all right? I don't want to get into that in 3.6. But this one actually comes this way. So it does still look like a line right there, but it approaches from the bottom up. Then it comes here to the -1, and because of the multiplicity of 2, it looks like a parabola right there. Wait, no, I'm doing this all wrong. I was right the first time. Oh my gosh, you guys. I second-guessed myself. I thought the degree of this was odd, so I redid everything. But I was right the first time. The degree is even. Let's, one more time. Here we go. A little line through here. We go down and up, and we make our parabola at this one because the multiplicity is 2. And then finally, I get to the 3, and the 3 has a multiplicity of 3, which means it behaves like a cubic function here. So it does this kind of a thing. It doesn't go through like a smooth line. It does do like a little wiggle, all right? And guys, I hate how back and forth this went, so I'm going to explain it here. The reason I drew the ends this way that caused these to go the way that they did is because I know this is a positive lead coefficient, and I know that I have 1x here, 2 here, so that's 3 in total, plus another 3 is 6. This function has a degree of 6. So I know my end behavior, based on the fact that it's positive and degree even, is up and up. All right? So knowing that it was up and up is what made the rest of the chips fall where they did. Okay. Let's go back to number 1 now that we've had this mini lesson. Basically, this was a mini lesson on basically all of 3.6 and 3.7. All right, but go to 3.7 for more details on 3.7. Okay, back to here. If a 0 has odd multiplicity, the function passes through the x-axis. Look at it. When the multiplicity was 1 or 3, that was odd. So we went through because odd functions do have the up-down end behavior. See? So that causes it to go through. Whereas an even multiplicity means I'm looking like an even function right around that x-intercept, and even functions have like a down-down or an up-up end behavior, causing them to not actually get to go through, but rather to bounce. Okay? So odd multiplicity goes through. Even multiplicity bounces off the x-axis. Okay? All right. So always. Okay? If a 0 has an even multiplicity, the function will bounce off the x-axis. Oh my God, I literally just said that. Always. These two. Basically, put them in your notes. This is notes, all right? A multiplicity greater than 1 means that the function passes through. Well, here's a multiplicity greater than 1 that passes through. Here's a multiplicity greater than 1 that doesn't. So sometimes, not always, not never, but sometimes. Okay. Select all the functions with x-intercepts at these spots. Okay, you guys, we learned about this in class. So let's reiterate, all right? The x-intercepts that you see present in the equation with the opposite sign. So a -5, a -5 presents in my equation like x plus 5. A +1 presents in my equation like x minus 1. And a +6 presents in the equation like x minus 6. If I am to have these x-intercepts, I must have these factors over here. Now, could I have different leading coefficients? Yes, I could. Would it affect the x-intercepts? No, it would not. Could I have various multiplicities going on? Again, yes, you can. Does it affect the x-intercepts? No, it doesn't. So if my only condition is that the x-intercepts be here, any of these that show me this, this, and this are it. So let's see. X minus 5. Nope. I needed x plus 5. X minus 5, okay. X minus 1, okay. X minus 6, okay. This one's good. I don't care about these exponents. They're not affecting the x-intercepts. They're affecting the behavior of the function around the x-intercepts, but not the x-intercepts themselves, all right? Okay. My phone is threatening to die on me. Plug it in. Okay, let's look at this one. X plus 5. Wait a minute. Did I get thrown off? I saw this x minus 5, and I missed it that it was supposed to be an x plus 5. I got too excited about these two being right. This is wrong, you guys. It's supposed to be x plus 5. So right here, it's x plus 5. Check. Right here, it's x minus 1. Check. And x minus 6. Check. These powers don't matter. This is okay. Looking here, x plus 5, check. X minus 1, check. X minus 6, check. Alrighty, good. That's a negative. It's not going to change my x-intercepts. Plus 5, minus 1, minus 6. Okay, sorry. It is B, D, and E, you guys. Okay, looking here. Here's the graph of this function. Which of the following equations could represent f of x? Let's go see, all right? The first thing I noticed that it's positive, and I do try to eliminate stuff the easiest possible way I can, but they didn't give me any negatives, so that didn't help. Looking at this, and it is kind of small. Can I adjust where it zooms to? No, I guess I can't. Okay. Looking at this, you guys, I am going through -2. I am going through 0. I'm also going through 1. Now let's talk multiplicities. At -2, gosh, it's so tiny. Why did they make it so tiny? That's so annoying. You guys, if you like really inspect it with like a microscope, I see a wiggle. I don't see a line going through. I see a little wiggle. Okay, that tells me the multiplicity is 3 or higher. Because remember, a multiplicity of 1 is linear. Is a line. Lines don't wiggle. Okay. Looking at the 0, that one looks like it just goes through straight like a line. So I would call that a multiplicity of 1. And then the 1, holy moly, I would call that parabolic. Like it does look like a little parabola right there. Okay? Again, why so small? I don't know. 2. So here's what I'm looking for. I'm looking for the opposite of these numbers. I'm looking for an x plus 2 with an exponent of 3 or higher but odd. I'm looking for a, okay, 0 means x minus 0, which also just looks like x, with a power of 1. And I'm looking for an x minus 1 with a power of 2 or higher, but even, but I would not, I would think just 2. So let's go see what we got. X plus 2 to the third. This one has it. That one to the second, no way. That goes through, absolutely not. That one to the third, but it's plus instead of minus, so no. Plus instead of minus, so no. It looks like it's going to have to be A. But let's see. Is there an x to the first power? Yes, there is. X minus 1. Wait, what? What did I do wrong? Wait, why am I saying x minus 2 is okay? You guys, I am so sorry. I don't know what's going on with my head. All right, I need an x plus 2 to the third, so this is not good. X plus 2 to the third is this guy, followed by an x, followed by an x minus 1 squared. It's C, all right? Okay, my eyes are dancing around. Okay, let's keep going. Fill in the blanks so that the polynomial will have the behavior shown at each x-intercept. Okay. At the -4 x-intercept, which is right here, I see a parabola, the behavior of a parabola, so this should be squared. And then at the x, oh, over here, I have another parabola, so they've already put the square there for me. But where is this one? This one is at 3, which means in the equation it'll be minus 3. Okay? And over here, at 0, I have a parabola. That's what that x squared is. But at -2, I'm looking pretty linear. So I would need a +2 and then to the first power. Okay? All right. Let's go see what else we got. Number 8. Oh, we're still doing this. Okay. Teeny tiny graph. All right, I see x-intercepts at -4. I see an x-intercept at -1. I see an x-intercept at 5. All right, at -4, the x-intercept I see looks quadratic. So this is going to be an x plus 4 squared. At -1, it appears to be like a line just going through. So that should have an x plus 1 to the first power. And then finally, here I should have x minus 5. And that also looks like a parabola, so squared. Okay, so let's go see. Plus with a square, it's got to be the 4 right here. Plus with a 1 as an exponent, that's got to be my 1. And then x minus, that's going to need to be a 5. Okay, and I put 2 because this looks quadratic, but we've seen that like 4th degrees also can look like these. So that's why earlier, when we were on this problem, I was saying it can be 3 or more as long as it's odd. It can be 2 or more as long as it's even. That's the deal with the multiplicities, all right? So on this one, it just so happens that it's a 4. So we put 2, but it could be more as long as it's even. So 4, it's fine. This is fine. Okay. The graph of the function p of x has these features. It passes through the x-axis at -9 and 0, has a multiplicity of 2 at 4. Write a possible factored form equation. Okay. It's called p of x. Okay. It goes through the x-axis at -9. That means we have x plus 9 as a 0. As a factor. And then I could put any odd exponent right there. I'm going to keep it 1 until I'm forced to do otherwise. It also passes through at x equals 0. That means I've got x. Again with an odd degree because we're going through. So some odd exponent here, I'm going to keep it 1 until they force me to do something else. And then lastly, at 4, so with x minus 4, we have a multiplicity of 2, so that's a 2. Okay. Write a different possible factored form equation. No problem. I can write a million. I can make it negative. It would not change. It would not change my x-intercepts, all right? Or the behavior of whether they go through it or not. What else I could have done is to put different odd exponents on these two, because they did give me a lot of freedom when it came to those two and their multiplicities. Okay, this polynomial has a 0 with a multiplicity of at least 1. The polynomial has a 0. Oh, this polynomial. Whew, sorry. Okay, moving on. So that was it. That was it for this one. 9 and 10, we're done there. Now we're looking at 11. 11 says this polynomial has a 0 with a multiplicity of at least 1. You guys, zeros, if they're real, they're x-intercepts. Look at that lonely x-intercept. I disagree. I disagree. Okay, this guy has no zeros. No real ones anyway. No zeros. Okay, now we can argue imaginary ones, but that wouldn't make sense either. If there was an imaginary zero, I mean, there are imaginary zeros, and they'd be in conjugate pairs. Let's pretend it's talking about real ones and that we disagree. Okay, however, you could potentially agree and say that this guy does have imaginary or complex zeros. Okay, so I don't know. If you justify it properly, I guess you may be able to get away with it. I don't know. Spiral review, we're talking about end behavior. Write the end behavior of these guys. So important, you guys, because end behavior is a big part of what we're doing in 3-7. So make sure you know it. Look how gloriously the spiral review is reminding you of what you need coming up. This is a positive even function. All right, here we go. We have negative. And we have positive. Okay, I ran out of room, so I couldn't write out positive. And then we also have even, and we have odd. If a polynomial is even and negative, it has this kind of end behavior. If it's even and positive, it has that kind of end behavior. If it's odd and negative, it has this kind of end behavior. And if it's odd and positive, it has that kind of end behavior. Okay? So this guy is positive and even. So that kind. So on the left side, we are going up. On the right side, we are still going up. This guy is negative and odd. Okay, so negative and odd, negative odd, has this kind of end behavior, meaning on the left side, I'm going up. On the right side, I'm now going down. This guy, they're being rude, just flat out rude, all right? They want us to write functions in standard form, and they're going to give us one that's not in standard form. Make sure you're on your toes, guys. The leading term is that one, because that's the one with the biggest exponent. So this is right here what I'm looking at. So my degree is 6, meaning even. And my leading coefficient is negative, because it's a -2. All right? So coming here and looking at what even negative looks like, it's down on the left, down on the right. So left side, down. Right side, still down. Negative infinity for both. All right?